Okay, so today we're going to talk about chill water system optimization. All right, to me that is usually a really boring topic. Why? Because people talk about their own system. We do, there's like Optimum Energy or Siemens has their demand flow, and I think some of these other, I think JCI has something. I think these different organizations have their own chiller optimization program, and then they just talk about how they saved all this energy and have a great payback, and it's like, well, that's not what we're doing here. And so what we're doing here is, I believe we're going to find ways that we can look around at the chiller plant, and we, being normal people who don't want to, sign up for some big program, can actually make changes and save our clients a lot of money. This is useful to us M&B people because, gosh, the best thing you can do in M&B is find a really little tweak and save your customers tons of money, and then maybe rescue any failing M&B jobs you guys have. Okay, so Duane, I'm going to briefly introduce Duane. Duane's not very good introduction, but he's going to finish the introduction. And basically, I ran across Duane. I'm on the editorial board, whatever that means. I guess that means something. I read the articles for the International Journal of Energy Management, and I was reading all the articles for the last year, and Duane's 2 articles, I thought they were the best 2 articles of the year. That's so once I really like this one. He did this one, and he did one, I think it was on retro commissioning or something. I think that was retro commissioning, right, Duane? Is that right?
Yep. Yes, sir. Yep.
Okay. So, but this one I really liked. I thought it was really good, and I thought it'd be a great webinar, and here we are. So what I like about Duane is he speaks in a way that normal people can understand. Normal meaning we're not PhDs. Yeah, we may be smart, we may be engineers, but we're not PhDs. And as Duane just said, what was it you said? Einstein said this or something. What was it?
Yeah, if you can't explain it simply, you don't understand it.
I am in total agreement. Okay, Duane, introduce yourself.
Okay, so I am, let's see if I can get this slide going. There's us, and this is me. So I'm a Texan, live just outside of Dallas. I've been here about 12 years, lived and worked in California for about 10 years. Originally, I'm from Canada. Once in a while, you catch that in my accent. I've installed and commissioned chill water systems for probably 30 odd years or so. I have a patent for one type of chill water optimization. That's from my time with the demand flow group, and long since gone past that. I have a trademark for another type. And I do mechanical commissioning for JLL, BMS testing, some consulting. I do ground fault issues and communication issues. I tend to do a lot of that. I get involved with harmonic analysis and vibration testing. And I do some internal and external training inside and outside of JLL. So for today, what we're going to talk about, what's optimization? What are we trying to do with it? How does it work? How can you make it work in your plant? How do you implement it? And what do you have to do to keep it working? This stuff is pretty, as you go through it bit by bit, it's pretty straightforward. And this is an example of a site, just to give you an idea of what the implementation looked like. When we went on this site, it was an air-cooled chiller plant, and it was running at about 0.8 kW per ton. And you could see right around 8 o'clock in the morning, we went down to about 0.48. That's all in chillers, pumps, and air handlers. So chilled water system optimization includes air handlers. Doesn't do any good to optimize the chiller plant if you're giving the air handlers a headache and making the space temperature go all crazy. You'll notice down at the bottom that the delta T went from 8 degrees right up to around 15 degrees. It was a 12-degree design system, 12-degree delta T design, and we kept adjusting pump speeds and monitoring valve positions on the air handlers to try to get to a point where if we went any further, we dropped the pump speed down any further, it really didn't make any difference to the air handler. It didn't make any difference to the chiller or the kW per ton values. And we're going to talk about how we go through this process a little bit later on, but I just wanted to give you a little bit of a flavor of what you can expect to see when you're going through implementation. You notice that the squiggly orange line in the middle is the average space temperature. Stayed right around 70. So for that plant, we went through integrated systems test, and you can see the baseline and the optimized kW per ton values are quite a bit different. We're down around 0.6. At 100%, we're down around 0.5 all in kW per ton, as opposed to around 0.8 all in. And you can see that it's fairly flat as well, even at the 25% level. It's 25% load, it's still fairly flat. Lots of lines on that one, but basically same sort of thing. PUE, we do, you know, you're going to hear a lot about PUE, or you do hear a lot about PUE. People ask for that as a measurement tool. I'm not so keen on it, mostly because if you look at a data hall, you'll see that when you're looking at the servers in a data hall, the total fan energy of all of those servers is actually a lot more than the fan energy, and sometimes it's even more than part of the chiller load.
Hey, Duane,
yeah.
let me interrupt for 1 sec. Some folks might not know what PUE is. Can you explain what it is first?
Yeah. So PUE is a power use efficiency ratio, and it's a way of saying, hey, what is the total power used by the facility divided by the total load on the data hall, and if you're not, so it's a way of more or less saying, hey, how much mechanical load, how much electricity am I using to generate the mechanical load and lighting and other things as compared to what's inside the data hall.
Yeah, and this is for data centers.
It's just for data centers. And I wanted to show this. It's probably going down in weeds a little bit too much for data centers, but I just wanted to show this so you can see that hey, this process works for something like a data center, where you would say, hey, how do I make a data center more efficient? And it's probably one of the harder things to do, is to try to make a data center more efficient. So, you know, a process load, and this is one of the ways to do it. So what happens in a system is you'll see an air handler, and it's sending heat to a pump, and the pump is sending heat to a chiller, and the chiller sending heat to a condenser water, and it's going through out through cooling water, and all of those, or through a cooling tower, and all of those things have different sorts of energy levels, right? So really what we want to do is we want to change this a little bit so that this kind of works like a siphon. We want to siphon heat out of the system without adding in supplemental energy along the way. And we want to siphon out of the air handler, just siphon it through the chiller, through the condenser pump. And that's really what we want to do. We want to see if we can find ways to deal with all of the inefficiencies that happen with the equipment along the way. And what we're trying to do as well is we're trying to find a way to get the system to operate in a manner so that it's efficient throughout its range, not just at full load, but also at part load, so that generally speaking, that the efficiency is about the same or very close to the same in the summer, where it's got to pull a lot of load, and in the winter where it's got just a little kitten there purring away, and back to Mr. Leopard spring and fall, when it's got to speed up and slow down significantly. And really, you know, generally speaking, you're going to see a chart, your chiller plant somewhere on this chart, and we see a lot of plants somewhere around 0.9 to around 1.2 kilowatts per ton. We want them to, where we really want them to be is we want them to be down in that area. New construction about 0.5. That's for new construction. They generally are 0.4, 0.55. And if we're going to retrofit them, they start at around 0.95. We want to get them down into that range below new construction. And that's possible to do with, if the chillers are, let's say, 15 to 20 years old or newer, it's definitely possible to do. So right now you see all kinds of optimization programs out on the market. There's a bunch of them. Hartman Loop, CPO 30, which is now Hartman Loop is marketed through Johnson Controls and licensed to them. CPO 30 is Hartman Loop, and now they have another program. I think it's called CPO 50, and it's another version of the Hartman Loop. Earthwise is trains. Harmony is the one that I have the patent on. Demand Flow is a Siemens product. Optimizer is Carrier's version of optimization. And they all basically do the same thing. I would say some of them do it a little differently, and I'm not 100% convinced that. Well, let me just say this: that engineering is the art of the simplest thing that works correctly. And so I believe that systems that are supposed to control complex things like chiller plants and chill water systems, they should do it in a simple manner, not a really complex manner. And so we have some goals here. We want to, when we're building this, we want to increase reliability. We want to make sure that what we're doing is measurable, that it's repeatable and durable. It's not going to fall apart a year after we're gone. That it's platform independent. There's no mysterious little black box or some other remote control thing that you don't know what's happening, and you sit on the sidelines chewing your fingernails trying to figure out whether or not it's working right or not. Should be understandable, and it should reduce mechanical utility costs by somewhere in the range of 20 to 40%. That's what we're looking for. So how does it work? Well, we've got some physics here, and not surprisingly, energy moves from warmer objects to cooler objects, and we try to get a good temperature difference. If you've got a nice high delta T, which is what the system's designed for, you'll find that energy is going to move faster than it would with a lower delta T. And that's old log mean delta T, can't get away from that guy. If you slow down the chill water flow, it makes the return water warmer and it has a better chance to absorb heat from the air inside the air handler more efficiently. And it also has a better chance of transferring energy inside the chiller.
Okay, so I want to interrupt again. Most of you know this, but just in case you don't, the delta T is the difference between the chill water supply and the chill water return temperature. And you want a higher delta T. What do you want? 10, 12 degrees, something like that?
Most systems are designed at 12. Some were designed at 16. You can keep it up around that design. That's pretty good. It's not unusual to see them when we walk into a building. It's not unusual to see them running at 4 degrees, designed for 12 and running at 4.
I've been seeing them at 1 and 2. Yeah.
Yeah, that's hard. It's hard for the system to operate. And we're going to talk about that right in a few minutes. So this log mean delta T. So this is a little thing here that shows what happens with the chiller, or sorry, with a 50-ton air handler. It needs 80 GPM with a 15-degree delta T. In theory, at 30 tons, it only needs 48 GPM. But if you've got an 8-degree delta T, the efficiency loss bumps it up to around 60 GPM. So you got to pump more water just because you have a lower delta T. And that's got to do with the reduced heat transfer at the lower delta T. So you keep that keep that delta T up, and you'll have a much better heat transfer, a much better chance of making that work properly. Now we've got a air handler here, and this is really where it starts to rubber really starts to meet the road here. So let's take a look at that. We've got an air handler coil at design condition, and you can see the airflow moving from left to right through the 6-row coil. Red is the incoming side, blue is where the air is going out the coldest. And you can see airflow going from left to right, and you can see the dry bulb temperature dropping. It's dry bulb temperature is going from somewhere around 75 degrees, and it's going somewhere down to around 54 or something like that. 52, there you go. And so you can see the dew point drop off, and if you can see that most of the moisture is coming out in the last two rows of the air handler. Water content really, it's in the last row, which is really what you want. And so that everything's working okay. You got about 1.1 million sensible BTUs, around 250,000 latent BTUs of cooling. Now, all of a sudden, we have a low delta T issue on the right-hand side. Look what happens. Now we have colder water on the first row of the coil that the air sees. That's the one on the left-hand side. And so now we've got colder water there, so that means it's going to start to dehumidify faster. And now dehumidification is occurring on the third row, third, fourth, and fifth. Is that right? Third, fourth, and fifth rows, yeah. The last 4 rows, it's dehumidifying a lot more. So, not surprisingly, we got 1.5 million total BTUs because we're taking out more moisture than we were before. Still got the 52-degree dry bulb. It's about the same. Dry bulb's about the same. But look how much moisture we're taking out, which we don't want to do. So if we can get the delta T back up, that means that the water that air sees on that first row on the left-hand side is going to be warmer, and it's not going to dehumidify as much.
This confuses me because out in the southeast and probably where you live, dehumidification is what they want. Well, what am I missing here?
You want that, but you want it to happen in a controlled manner, right? So you design the coil and you select the coil to get the condition that you want, and that dehumidification is going to occur in the last 2 rows. But if you have excess dehumidification, you're going to have the air coming out a lot drier than what you planned on, and you're going to use a lot more energy that really is going to cause 2 problems. Well, 3. The first one is you're going to use more energy than you planned. The second one is that if from a tenant comfort point of view, instead of having 55-degree or 52-degree dry bulb supply and 51.8-degree wet bulb, now you're going to be way down. You're going to be 52-degree dry bulb supply, and the wet bulb's going to be like, 46. Not so good. It's going to feel cold.
Got it.
Even though the dry bulb's okay, the moisture content is down, so you're going to feel cold. Now, there's one other hidden problem here, apart from the increased energy use, which is significant. Like that's 40% more energy. The dehumidification is now occurring on the inside rows of the coil. Well, when the poor maintenance guy goes to try to clean the coil off, instead of just cleaning off the last row or 2, which is pretty easy to do, now he's got to clean off the middle rows of the coil, which is extremely hard to do. And really, most cleaning efforts, when they go to clean a coil, when they try to get at the middle rows, it doesn't actually clean it, it just pushes the dirt further in. So this is actually creating an air restriction problem over time that we want to try to avoid. We do that by looking at variable pump control. And we control that pump speed, the delta P, and we vary the pump speed throughout the year. And we do that in a manner to make sure that we have a reasonable delta T on the chiller. We don't go below the minimum flow rate for the chiller, but we do try to run at a spot where we can get the delta T in the chiller correct, and we're not starving the air handlers. So we look at valve position on the air handlers, and we try to see if we can keep those valves at somewhere around 80 to 90% open. And really that's what we're trying to do by varying pump speed. Try to keep the valves on the air handler somewhere around 80 to 90% open. They're still in control. You know, you don't have them running at 100%. They're still in control, and you've got a nice good delta T on the chiller.
Huh. So then you have some kind of control strategy it's varying the pump not based on differential pressure. What is it varying it on? Or
It changes the DP set point based on valve position.
Got it.
And that is a so that is a there's actually a flow chart for this, and I'll send that to you folks, John. So you'll see the flow chart for it. It's pretty straightforward.
Is there a name for this strategy of varying chill water speed?
I don't really. I've called it harmony, but it's in one form or another. It's been around for a little while, and PIC valves sort of do this. We're going to talk about that in a minute. Actually, I think that's the next slide. Why not use a PIC V, process independent control valve? So what a PIC valve does is it looks at the coil temperature and says, hey, coil temperature isn't really kind of isn't really that great. I think I'll just slow the flow down, and it slows the flow down to get the delta T on the coil right. I don't like PIC valves because they tend to just increase system pressure, and they don't do as much at the chiller as I'd like to see, and they also require a fairly they need at least 8 to 10 psi to operate correctly. The 8 to 10 psi delta P on the system. And you're going to find that when you're resetting the flow to try to find what is the lowest flow or lowest delta P that's acceptable to the system, you might find when you're resetting it that you're going to have a delta P down in the, anywhere between 3 to 5 psi range at the lower end, and as high as whatever the original balancing contractor set point was. So it might reset between 4 psi all the way up to 20 psi, depending on valve position. And really, you're resetting that just to try to keep the air handler valves somewhere around 85 to 95% open. Which air handler valves? Well, that is a very good question. Let's go back to this for a minute. So when you're talking about which air handler valves, well, really you want the ones that are going to be more responsive to changes in load conditions. An earlier version of this and demand flow looks at all the valves in the building. I don't think you really need to do that. That's more complex than it needs to be. So Mother Nature gives us a little bit of a hint. Generally speaking, floors that are, if you're dealing with a multi-floor building, the upper floors tend to require more cooling because they have a roof load. And if you can look at the zones in the cardinal directions, north, east, southwest, northwest, east, west, the corners of the building. So now you've got 8 zones that you can pick. And I would probably pick another 4 to 6 other zones in the building that might turn out to be ones that tend to need a little bit more cooling. Might be a conference room, one of the internal rooms, might be something like a corporate office or something like that. And pick those rooms and use the system to look at the valve positions in those air handlers. You're going to see in a few minutes, you're going to see what that looks like. So this is a PID loop. And you could say, well, why don't we just use a PID loop to set the delta P control and just worry about it that way, and or have it handled that way. And really, the problem with PID is that there's someone hitting baskets like I wish I could. Notice that the basket never changes position. Well, if the target's moving and there's a goalie in the way, things are a little different in the real world. And changing conditions at air handlers, changing conditions at on the building, cause the PID loop to not function quite exactly right. And so what you want to do is you want to adjust that delta P up and down by incrementally by half a PSI or 1 PSI increments, and look to have the system look to see what the result of that is. It's more likely to prevent overshoot if you do it that way, and it generally looks a little bit like artificial intelligence, and that's because that's kind of how you would do it if you were trying to figure out what delta P to use. You would look at the air handlers and you would look at their valves and you would say, the valves are closing off. I think I'll just drop the delta P down half a PSI and see what happens. And then you'd look at that and see what the result was, and then you would change it a little bit more, another half PSI and then another half PSI. And you would continue to do that until you got the system operating at a point that you were happy with. So we want to look at the zones and figure out which ones are important, and look at air handler output call, fan speed, cooling valve position, things of that nature, to give you an idea of the cooling load from those zones. And it turns out that you have something that looks a lot like this. And this is from an active hospital. And so we've got a number of air handler output calls. That's coming. Those are calls from the VAD boxes. That's column number 1, 2, 3, 4, 5, 6 air handler output calls. You can see the first one is 52%. It's calling, it's mid-range, about 52%. And the fan impact is a way of saying, hey, how much is that fan actually? Is it speeding up or slowing down? Is it trying to handle static pressure problems because there's an increased load on the zone? Things of that nature. Next one over is cooling valve impact, and it says, hey, let's see what happens. What's going on with the valves? I want the valves to be around 55 or 85 to 90% on average. And this one isn't bad. You can see most of them are, they're up there. There's a few that are kind of closed, but their size is kind of small, and their impact range, like an operating suite, it's not as important as the operating suite. So we tend to make that one a little bit more important. And so what's happening is this control loop here is looking at valve position, and it's making a decision. It's going to say, hey, I'm going to, based on the valve positions that I see, what I'm going to do is I'm going to either increase or decrease the delta P set point by a small amount, a half a PSI or 1 PSI. I'm going to wait a few minutes, probably 10 or 15 minutes for everything in the system to stabilize. Then I'm going to change it again, and then I'm going to change it again. It looks at fan impact and the air handler output call to give it an idea. This particular control thought process looks at fan impact and air handler output call from the VAD boxes to give it some advance notice. So that's a way of saying, eventually, if the fan is speeding up, it's because there's increased load. Eventually, if the air handler output calls are increasing, I'm going to get increased load, and that will cause the valve to open up. So I'm going to use a little bit of that information to impact what's going on with the amount of delta P change that I'm going to make. Those first two, air handler output call and fan impact, are more about feed forward control and being in advance of what's going to happen. Cooling valve impact is really the only one that is very important to pay attention to. That's the one, that's where all the money is. If you can keep those valves at around 85 to 95% open, you're in good shape. The other ones are more about, in this case, we had some operating suites, and we wanted to, the reason why we had that here is that what this owner wanted to do is they said, hey, when we start using an operating suite, we're going to clean it out first before we put people in there. And when we clean it out and start putting load on there, we want the system to have the suite to respond to all of that activity and water and whatever else they're doing in there, all that increased load. We want the system to be able to respond to that so that when we wheel a patient in, it's exactly the temperature we need it to be. So we needed to know, we need to have a way to know in advance what was happening from that suite, not have it react. We needed some feed forward control. So that's why this is the way it is. But this is an Excel spreadsheet. One of the advantages of having this as an Excel spreadsheet is that I expect that the BMS contractor is going to put this in as graphic. And so far, Johnson Controls does it, Automated Logic does it, and Honeywell does it. It exists in their world. This graphic, exactly, and this calculation, exactly, exists in their world. So, and you have that same, when you're doing commissioning, you have that same Excel spreadsheet. So when you're checking out their system operation, you can either fat finger the numbers in or have it ported in from their system directly into Excel, and you can see whether or not their system is operating correctly. You're going to know pretty quick because even without checking it, you're going to know pretty quick. In this case here, I've got an operating suite that when I was doing this capture, the operating suite had just started to get cleaned up, and so they had a pretty big call out for load. So it's going to start driving the system open and driving the delta P down and things like that, or delta P up, pardon me, get more flow. So again, cooling valves are one that you really want to pay attention to. Low delta T affects the chiller too, and so apart from the heat transfer, if you take a look at this cutaway view of the chiller, you notice some green arrows, and it looks like it's going through green arrows in the evaporator at the bottom. It looks like it's going through something that looks like a colander or a sieve, and it actually is. That's the eliminator plate. And the eliminator plate sits above the refrigerant bath, and all the water tubing is below that. So the water tubing is inside the refrigerant bath. The eliminator plate is right up above there. And what its purpose is for in the chiller is it's there to protect the compressor so that it doesn't get either oil droplets or liquid refrigerant droplets coming into the chiller intake. These exist on all chillers. This one's on a centrifugal, but it exists on screw chillers and whatever other kind of chiller you have. They all have an eliminator plate. And so there's always some oil mixed in with refrigerant. When the oil hits the eliminator plate, the holes in the plate are really small and it just atomizes it. Makes a pressure, there's a pressure drop, it just atomizes the oil. If there's liquid refrigerant hitting it, which there shouldn't be if the delta T is operating correctly in the chiller, if there's liquid refrigerant in there, what happens is the liquid refrigerant hits the eliminator plate, and because the holes are small and there's a pressure drop, it evaporates the refrigerant and atomizes it and evaporates it. So if you have a low delta T operating on your chiller, you know, let's say around, if it's designed for 12 degrees and it's running at 6, you're getting about 6 degrees of evaporation occurring on the eliminator plate, which is not in contact with the chill water at all. That eliminator plate is I guarantee if that's happening, it is the coldest thing in the entire system. And it is just sitting there like the world's biggest wind instrument, taking in liquid droplets, liquid refrigerant droplets, and atomizing them. Now you can actually get to a point where the delta T gets so low that the eliminator plate gets overloaded and liquid gets pushed through it, and you start to have stall problems at the chiller or perhaps even a low end surge. Don't like that at all. If you can get the delta T back down, or sorry, back up, you get the delta T up to a point where it's at design or higher, the liquid refrigerant is evaporating before it gets to that eliminator plate. So we want that delta T to get back to normal and try and keep it at design as much as we can. Little trick though with this one. There's a neat little trick. The chiller's designed for 12 degree delta T. If I get 14 degree delta T out of it, what I'm doing, the chiller manufacturer assumes that some of that liquid refrigerant is going to hit the eliminator plate and evaporate there. It's baked into how they design the chiller. They assume it's going to operate inefficiently slightly. So if I run a 12 degree delta T chiller at 14 degrees, I'm starving that eliminator plate. I'm removing any of that liquid refrigerant that they have baked into their design that they assume is going to be wasted. So I'm increasing the efficiency in the chiller output. There's the sieve again. And if you actually, I have actually done this a few times. I'm an ex-chiller mechanic. So I've had to replace the refrigerant, or sorry, the insulation on a chiller barrel. And you can actually see it when it's running at a low delta T. You can see where the eliminator plate is. You can take a thermal gun and you can figure out where it is right there. And so when we look at a flooded chiller barrel, it's kind of an older one. This has got a McKinstry logo on it. It's one of their jobs that I did for them. It's got a flooded chiller barrel, 12 degree design, 6 degree actual delta T. And you can see that the inlet screen and the compressor inlet are taking some of they're taking up some of the evaporation, and the liquid refrigerant, there's some liquid refrigerant that's being dealt with at the inlet screen and the compressor inlet. So it's just kind of wasted. If we can get it over to the right-hand side with a barrel at 12 degrees with a 12 degree design and 12 degree actual, there really isn't very much in the way of refrigerant that's being evaporated at the inlet screen. That's over on the lower right-hand side. It's a very small amount as compared to on the left-hand side, it's up around, looks like it's around 45%. Now, some evaporators, the newer ones, use falling film instead of flooded. That's not much different, really. Not much different. The falling film, instead of having evaporator fully flooded, there's liquid or droplets that run down the center part and they're sort of sprayed out across the tubes. And then down at the bottom, there are some tubes that are water tubes that are sitting in a refrigerant bath, and that boils off and it goes in through the intakes on the side of the machine. Good news, there's way less refrigerant use with falling film, probably about half the refrigerant in this type of evaporator for the same cooling effect. Much smaller chiller barrel, and so fits in a smaller area. Drawbacks. You see the little blue area down at the bottom, that's the liquid level. If you get a low load on the chiller, that liquid level is going to start to rise up. And if it rises up just a little bit, right up above the two lips, right on each side, there's little white pieces of metal on the side, right next to the tubes. If it rises right up above there, what happens is you have the liquid seal now, and so the evaporated refrigerant that's in the falling film area, it can't get out. And so what it'll start to do, the pressure will build up in there. It'll build up, and then it'll bubble through and sort of force the liquid aside and push the liquid out. So now you'll have some uneven flow going back to the chiller, and perhaps it'll have some liquid droplets in it too. But you'll have uneven flow. It'll have very little refrigerant, pressure will drop off right at the compressor intake, but it's going to build up inside the center portion, and then it's going to shoot right out. And you know, it'll build up, and then poof, it'll push it all out. Then it'll go back, and it'll push it up and go back, and that'll start a surge. So you can put hot gas bypass in to deal with that, or some control valves to deal with that. And bypass, usually use a bypass line. But if you control the flow, you can keep the flow control done properly. It'll be a lot easier in these chillers, and you'll be able to stage them a lot easier. And the staging will become a lot more predictable, a lot easier to operate. We do mention in here, if you're going to use control valves for bypass, to put two bypass valves in. That's a maintenance thing. One, having a bypass valve in there is a good idea, or some way to have maintenance around that bypass valve. Also, it's better for controllability purposes to have a couple of valves in there. The chiller's got some operating limits, and it just increases pressure in the refrigerant. It's got some gas flow. There's a motor current chugging away, and we got gas coming from the evaporator. The VFD can slow the chiller down, usually down to around 60%. It drops the compressor tip speed, and it keeps it. The minimum speed is basically you want to be able to stop the gases from moving backwards. That's really what you want. And below 50%, you can start to really have a problem with the compressor, because the pressure can build up inside the condenser, and you notice that we have every now and again you have the compressor blades moving backwards. That really doesn't happen all that much. If it started to happen a little bit and they started to move like that, the compressor would surge out and you'd bust compressor blades or burn out the motor or something like that. So 50% is kind of, 60% is kind of the minimum speed that you really want to operate these machines at. And the chiller manufacturers deal with that internally. That's internal to the machine, and that's how they make the thing work. So we have some rules for chill water flow. We don't send water out of the chiller plant unless the air handler zones need it. We want to keep the valves open around 90%. And we do that by varying delta P. We maintain enough minimum pressure to allow water to push through the chilled water valves. And we try to increase flow during stage up and down for stability. So you're going to come to a point where you have, partial flow, and you have to get a chiller running. So we might increase the flow for a little bit just to satisfy the needs for the other chiller, and then go back to delta P control again. I usually like to use demand limiting when I'm staging up and down, but you don't necessarily have to. That's up to you. I'll limit a chiller for limit 50%, and then stage the other chiller on, and then release demand limit after a few minutes. You want to stage up and down based on temperature and percent chiller load. Flow meters are nice. I like to see them. They're useful information, but not for staging. The money's in, am I setting temperature? Am I setting water temperature out? Do I have the valves working okay? If that's okay, then I'm meeting the load. And do I want to stage up and down? If the chillers are handling the load, I don't need to stage up. Now we're going to talk a little bit. Let's see if we're getting there. Yes, we are. Condenser water relief. That's the other side to this equation. So everybody noticed, I'm sure, that if you get colder condenser water, it reduces energy use of the chiller. It does increase chiller capacity slightly, 30% or something like that, as much as 40% maybe. It makes the chiller run quieter, but it's weather dependent. Sometimes you can do it, sometimes you can't. Depends on if it's hot or humid or windy or not. You can use analytics and feed forward control, which is what we do. I was actually part of an ASHRAE group that came up with a control process, and it looked to deal with condenser water temperature control, and it looked at humidity, and it looked at wind speed, and it looked at the sun, and it looked at temperature, looked at a number of other factors with a fairly expensive sensor array, and we were able to do it. But it turns out that there's a much simpler way that Mother Nature and physics helps us along with. We got to be able to maintain whatever temperature we maintain that condenser water at. We have to be able to maintain a difference of around 5 psi inside the chiller. You can go down to maybe 4 at full load, but you need 5 psi between the condenser and the evaporator bundle, and you need that because you have to be able to push the refrigerant through the expansion device. You need around 3 psi really, but 4 is kind of, I can live with 4. 3 makes me nervous, but 4 psi is probably, at full load is probably fine. 5 psi is pretty safe.
Hey, Duane, this is new to me, this 5 psi here. So do you have control strategies that are written that, you know, are looking at this delta T or delta psi and making adjustments?
You can do it that way. You can do it that way, but and that is a way to do it. But I would, and it is actually one of the ways that the Hartman loop does this. I'm not so keen on doing it that way. There's you're going to see in a minute why that is. So we've got some high condenser water temperature, and what happens at the expansion valve is we lose about 30% at the expansion device. 30% of the liquid refrigerant inside the condenser just flashes away to try to get the refrigerant down to a lower temperature. So if you can run lower condenser water temperature through there, you're going to have cooler liquid refrigerant, and you're not going to lose as much flash gas. That happens when you get down to 80% of that happens if you're running at 65-degree condenser water. And you are way higher than 5 psi delta on the difference between the refrigerant pressures. You're up around 7 or something like that. So you can go colder. You can get the condenser water to go down to 50 degrees if you want, and you can get like another 5% or maybe 8% out of the chiller capacity. But it's like small money. Like you're not really gonna. The conditions for that to occur don't happen very often. It's not cold enough for you to do that, and it's like you're chasing the last rabbit in the field when you already got 6 in your pocket. Don't worry about it. So we like to see if you make it too cold, you can have a problem where the liquid just sits inside the condenser bundle and it doesn't ever go in the evaporator, which we don't want. So this is what we do. We like to see, a minimum. The lowest you ever want to go is around 55 degrees, and you can make the condenser water speed operate to maintain that delta P if you want to do it that way. You can vary the condenser water pump speed, and it'll allow that refrigerant, or so it'll allow that water to slow down so you can keep that bundle warm enough, that condenser bundle warm enough, and keep the gas pressure warm enough to be able to push liquid through the expansion valve. So 2 things are happening at the same time. One is you're dropping the condenser water temperature down. Condenser water speed, condenser water pump speed slows down a little bit just to kind of control what's happening with the delta P. Now, you can control that off of refrigerant pressure. So you would have 2 refrigerant sensors, refrigerant pressure sensors if you want, or you can control it off the delta T difference between the condenser bundle and the evaporator. Notice here, condenser water temperature is 55 degrees. That's for a chiller with a 42-degree supply. 13-degree delta T between the condenser bundle and leaving evaporator temperature. 13 to 15 degrees is a pretty good number. There are some limitations. So chew gum and walk at the same time. You got to meet minimum water flow in the condenser. That's true. Got to meet minimum water flow in the cooling tower. Also true. we don't really have those as being real big problems. You don't ever go down that low, but it is something to keep in mind.
Hey, Duane, we probably should stop. Unfortunately, I know you got more to do. Can you just like summarize what's left in like 30 seconds? Because a lot of these folks got to go to meetings and stuff.
Sure. So we want to get tower water down to around, you can see what happens with tower water there. It's cold enough. This is there's a little thing in here on resetting chill water temperature that you have to be a little bit careful of. Sometimes the chiller KW goes up, goes down, but it also causes problems for fan energy use. And so we get a little concerned about that. And there is there's a section in here that I really want to talk about, a little bit about commissioning. This is a commissioning function, and it's about watching things work and how things happen over time and how they go slow enough to make how they operate slowly. And you just have to be able to sit there and watch things happen. You guys don't want energy to go back up. We want it to keep going down. And I think calibration and so on, we do want to keep it working by calibrating it. So there are some flow charts that I'm going to send to you guys, and that Excel spreadsheet that I'm going to send to Abraxas, and you guys can deal with people who, or how do you guys want to do that? You want me to send it to you, John? Or?
You send to us, and then if people want to see it, they can email us at webinars@abraxasenergy.com, and we can pass it on to them. I'm going to go over a couple questions. So one was, someone asked, isn't the critical parameter on chiller efficiency the lift?
Yeah, you want to maintain 4 to 5 PSI lift.
Oh, and that's exactly what you're just talking about. In the condensing scenario, a low delta T graph, how does a dew point fall before the dry bulb? Is there some bypass and remixing occurring?
No, it's happening because because you're essentially turning when you get a low delta T on the air handler, you're essentially turning it into a dehumidifier. You're putting colder water through the coil on the incoming coil surfaces, and that's how a dehumidifier works.
Okay, here's one. Can I reset the DPT set point? What's that? Delta. What's PT?
Delta P. Yep.
Oh, delta. It says DBPT. So I reset the DPT set point based on return temperature sensor if I don't have visibility to the valves.
I wouldn't recommend it, because what happens is that when you get low delta T, the air handlers pick up dehumidification load, and you're happily dehumidifying like a madman, and it looks like a load, but it's not really something that you want as a load. So you really want to, if you don't have visibility to the valves, you could try to do it off of outdoor air. You could do it that way.
Okay.
Yep.
Here's another one. So unfortunately, some of these questions were like they were asked at specific slides, like this one. 50% on cooling valve impact means the valve is open 50%. Is that right?
Yes. Yes.
Here's one. This 5 psi an absolute pressure in the condenser, or a delta P for delta pressure between condenser and evaporator?
The delta P between condenser and evaporator.
Okay, another one. ASHRAE guideline 36 recommends to start with chill water supply reset and then DPT reset. What are your thoughts on that? How will resetting the chill water supply temperature impact the dehumidification of the coil?
I love guideline 36. I think it's great for fan powered boxes and terminal boxes, but it misses a few things when you're dealing with certain climates, and that's a fact. Would you really want to do chilled water reset in the southern states first, where there's a humidity problem? No. Right. Northern states, sure. So, yeah.
That's good. Do you recommend varying the condenser water flow rate, pumps, VFD? How?
We would like to see that so it maintains the delta T difference between the leaving condenser water and leaving chilled water.
Okay.
So we want to maintain that you know, if we've got 55-degree water going into the condenser, sorry, leaving cooling tower. We've got 55-degree water going in, and 42-degree chill water going out. We got a 13-degree delta T. We're maintaining 13 to 15 degrees. Under full load, you can probably squeeze that down to 10, but we want to have those VFDs maintaining that delta T so that we've got enough pressure in the condenser to push the refrigerant through the expansion valve. And another way of thinking about this, we're subcooling the liquid in the condenser funnel. That whole process is removing subcooling, taking subcooling, just subcooling it like crazy.
Okay, on the condenser water control strategy Duane spoke of, is he also controlling tower fan speed or just condenser water pumps? All right. Yeah.
Both. Yep.
Okay.
And
that's the last one. Okay. Any last words before we move on to talking about the next webinars?
no, I'll send those flow charts and the spreadsheets through to you.
Okay, so I want to dummarize this for those who are more introductory, or let's say more, they're not as skilled as some of the folks on this webinar. The simplest things that someone could do or be mindful of course, is the delta T, the difference between chill water supply and return temperature,
Yep.
and seeing if you could slow down the flow so that that delta T will get closer to 10 or 12 or, you know, maybe even better. That would be the simplest thing. Go ahead, interrupt me, tell me.
That is absolutely right.
The second simplest thing, well, of course, is a condenser water reset. But you also mentioned, you said that you could slow down the condenser water loop. How do you control that, slowing that down? Oh, what's that control based on?
But we like to base that on what's the temperature difference between the condenser water temperature leaving the cooling tower and the condenser water temperature, or sorry, the chill water temperature leaving the chiller.
Oh,
So we want to
13 degrees.
Yeah, 13 degrees, 13 to 15 degrees we want to maintain.
Okay, that was missing. That was missing in my head. Okay, that's good. What would be the third simplest tactic for someone who's an M&V person and not a chiller pro to look for an easy change to a chiller plant?
I'd really want to look at how they're staged and really think about staging up or down based on our chiller load, percent load, and temperature.
I want to ask you one other question. This wasn't on their list or of the attendees list, but it's something that's confused me. So you look at some chillers like the turbo core types, the magnetic bearing chillers, or some of these other chillers, and they're really efficient at part load. But if you look at the chiller curves assume at part load that it's colder outside and the condenser water temperature is lower. So those aren't really accurate, let's say, curves, you know, because I would think I would want curves where it's always a certain temperature outside. It's always 90 degrees outside. Now the chiller is at 100% load, 90, 80, 70, 60, etc. And then we can see what the kilowatts per ton is. So two questions. One is your comments on that, and then the second part is I was originally used to believe that what you want to do if you have these kind of chillers is you run them all at part load. So let's say you had 5 of these. Let's say you had 5 turbo cores. You just run them all at you know, maybe at 20 or 30%. Run them all at 30% if you could, and then slowly, you know, ramp up whatever. But I was told by someone else that no, you need to actually, you want to run these, even if they are turbo cores, you want to run them near full load because of those curves. They're not telling the truth because of the differing condenser water temperature. So there's 2 different deals. Can you answer both of those or address both?
Yeah, so when we ask for chiller curves, when I ask for them, I always ask for operating what's the performance of the chiller at 25%, 50%, 75%, 100%, and then I'll ask for it at specific condenser water temperatures, 85, 75, 65, 55. And all of those percent loads at those condenser water temperatures. So I want to know if I'm going to run a chiller at 25% and it's 85 degrees outside, how's that chiller going to work? Now, used to be that it drove everybody crazy, but now they just run it through a computer model and it does what it's supposed to do. That is a very revealing. The results of that are very revealing from one manufacturer to another.
Right.
Very revealing.
The curves that are in eQuest or Trace, I mean, I think those curves are assuming lower condenser water temperatures. So then when you're using Trace or eQuest to try different scheduling or staging strategies, it's not really right.
It's not really right. It's not right, no. Now, the other thing that I just wanted to kind of let you know about that is important is that if you do run colder condenser water through the chiller, if you have, let's say, 1,000-ton chiller, and you run 55 degrees through condenser water through the chiller, you don't have a 1,000-ton chiller anymore. You have a 1,400-ton chiller because you're not losing flash gas.
eQuest isn't picking that up.
Doesn't pick that up at all, and that's why you want to change. You want to stage up and down a percent load if you're doing condenser relief, because if you got a 1,000-ton chiller and you're getting 1,200 tons out of it, why would you start another chiller? You got 200 free tons, right?
So back to what this guy told me. He's a chiller guy. That even if I had 5 turbo cores and I could run them all at 30, maybe it'd be better just to run 2 at full and 1 at something.
Yep.
Is that correct?
That is correct, and I do have to mention that part load operation of a motor is not very efficient from a electrical demand point of view, and definitely not from a harmonic energy generation point of view.
Okay.
VFD is certainly efficient, but a motor running at 50% is definitely not efficient from a KVA demand point of view, not at all. And these days, depends on where you are in the U.S., but in some cases the demand charge is 70% of the bill now. So
that's really bad news. I mean, you really need good chiller curves then in order to really look to be able to quantify what kind of savings you hope to get from staging. And I guess you're going to have to do this in Excel. And
yep.
Oh, that sucks. Okay.
Right. We do that.
Yeah, I believe you do that. Yeah.
We do that.
Okay. That was really good. Yeah. I mean, one thing I learned was how little I know. I'm often reminded of that, but today it was really ground into me. Thanks, everyone. Yep.